Log on, tune in, find out. Another good idea from Cambridge.
Next speaker is Hugo Maruri from Queen Mary University of London, and he's going to be talking about sequential screening with elementary effects.
Well, first of all, I'd like to take the opportunity to thank Rosemary and Basha as main organizers for the whole program. Also thank the organizers of this conference and thank the staff here at the Newton Institute who have been so helpful during what is going on, and they promise to be so during the rest of the program. What I am just about to present is some joint work with Alexis Bukubalas and John Paul Gosling, who were colleagues with me at the MUCM project. Now, Alexis at Aston University, John Paul Gosling at FERA, and well, my affiliation is Queen Mary University. Now, well, the abstract, I won't stop on that, is on the program. I would just start here. Well, I don't probably need to blow this trumpet that much, but well, complex computer simulators is part of a rapidly evolving field with numerous new applications springing, and here are just a few: climate projections, investigation of biological processes, and even estimation of national carbon balances. That is yours, Tony. Good. Emulators are built as surrogate alternatives to expensive computer simulators, and then instead of the simulator, we use the emulator for performing sensitivity analysis, predicting the response at new points, just to give a couple of uses of the emulator. Naturally, even in this setting in which the emulator plays a simpler model compared with the simulator, is still restricted to the number of input dimensions, and screening of input factors is required. So, just to mention a couple of screening alternatives that we have. A classical alternative, or well established, is the elementary effects method, first proposed by Max Morris. And there are other alternatives based on variance, which, for instance, the Sobol variance decomposition, but that would not necessarily be quite efficient. It only works directly when the simulator is a very cheap alternative and the sensitivity is performed directly there, so a large number of runs is required. Other alternative is the Fourier amplitude sensitivity test, also named as FAST, and an alternative of which I will mention later that was recently pointed to me, Jack, thanks, is the sequential bifurcation. Now, what this talk is about is we are looking for a sequential procedure for screening, and our aim is to separate input factors in two groups: those that have linear effects and those that have nonlinear effects. Now, in my goal, I just would like to do in what remains of my talk 5 things. One would be just to review the elementary effects method, then propose our sequential strategy. Then third, I will mention an example using the rabies model, then a high dimensional example, and finally the fifth, let you go for having your lunch. So, well, now I'm just describing what the elementary effects method for screening is. Let's assume y dot is the simulator is assumed to be a smooth function on k inputs, the usual design region. And now, at a point x, what we do is experimentation of the sort of one at a time, which means that I'm not that comfortable with the point x, probably best this. On the direction of the ith input variable, we move to a new design point, x plus delta ei, and then evaluate the simulator at that point. Then just take the difference with the simulator at the original point and divide by the increment, delta. This just looks pretty much like the definition of a derivative, doesn't it? But in fact, it's equivalent to fitting locally a linear, multilinear model, and then this would be precisely the slope. Now, The classic elementary effects method starts with a point x from which a trajectory is constructed. So from a given starting point, k moves are performed along the axis. So you move along one axis, then another axis, and then the selection of axes is random, but eventually the trajectory ends up in this point. Naturally, we have k plus 1 evaluations of the simulator, and we end up with k elementary effects, one per each input variable. That is performed, this is what is a trajectory. Now, consider a set of r points, and at each point of this design, you perform a trajectory. Now, once you have that, well, you have a collection of elementary effects per each input variable at each of these points in the design, and then you compute these moments. I must apologize that in all honesty, these should have hats, but they won't. But these are just the mean of those elementary effects and these variance. The sample moment is an average effect measure, and a high value suggests a dominant contribution of the ith input factor in positive or negative response values. It is considered that nonlinear and interaction effects are estimated with sigma I. Now, just to give a little bit of flavor, these are a couple of graphs that I stole from Alexis Bokubala's thesis. So this is one example of this elementary effects method. So for example, this was a starting point, and then this is one move along one of the input variables, another move along the other input variable. These moves are always along the axis. It's one at a time experimentation. Now, this is another trajectory, number 2, number 3, number 4, number 5. The input points are selected as part of a grid, and again, this is the traditional elementary effects. So it's no wonder why we are having that these two trajectories share at the beginning point the coordinate in x1. So that's no wonder at all. Good. At the end of these 5 trajectories, then the moments are computed, and you have, this is in the horizontal coordinate you have mu, and in the vertical you have sigma. So this corresponds to the moment of the elementary effects for the first input factor, for the second input factor. Now, there's been this moment mu I star, which is the average of absolute elementary effects, that has been suggested recently as an alternative to mu I, in that we could have a mu I that is 0 because of cancellation of effects, but that doesn't necessarily mean that the effects are negligible. Now, the total number of model runs required in this elementary effects method is, well, we have r starting points for each trajectory, and each trajectory has k plus 1 moves, so this is the number. Usually small values of r are used in his papers. Max Morris used r3 and r equals to 4, but then the work of Campolongo and colleagues suggests a value of r between 10 and 50. Naturally, the largest the value of r is, this improves the quality of the estimations, but at the price of extra runs. But I wouldn't say we are expecting quite a lot. Screening, we just want some qualitative assessment of where the factors are and which factors are interesting. Now, let me just say something more about the elementary effects method. So the step size delta, which is another of the ingredients, is selected. Well, firstly, we don't want the trajectories to go out of the design region. That's one of the goals. And that the elementary effects are computed with reasonable precision. In the paper, it's suggested to achieve this by using a k-dimensional grid constructed with p uniformly spaced values per input. And this was the sort of grid that was used in this example. The grid is not shown, but it was used. And then the number p is recommended to be even. Delta is a multiple of this quantity and set up to this as suggested in the paper. Now, the step delta is usually kept at the same value for all inputs, but there is no reason why we could use different step lengths among different dimensions. And okay, finally, points x1 to xr were taken at random from the input space grid. From that grid restricted to that was the selection of initial points from trajectories. But then in recent work by Campolongo and others, runs were spread over the design space by generating a large number of these trajectories and selecting a subset that maximizes the minimum distance between those trajectories. Now, as I said, I was not expecting a lot of this sort of method, but even if we want to do something else with these runs after performing a screening, a disadvantage of this method is that, well, we are doing experiments one at a time, so the projections fall into existing points when we are projecting on lower dimensions, and this might prevent recycling runs after the screening process. There's been an alternative to this, which is by Pujol and colleagues, which is to, instead of using these one at a time experiments, put randomly rotated simplexes. So instead of having a trajectory, we are putting simplexes at every of these points. Now, mu I star, sigma I are computed in a similar manner. Now, the elementary effects are defined as, again, as the slopes of the linear model fitted at each of these inputs. Okay, naturally, a potential disadvantage of this approach is loss of efficiency, as moving along the axis is optimal for estimating those parameters in the linear model. Now, this is our proposal. We just proposed to separate factors that have linear effect and those that have nonlinear effect. So, for achieving that, we use sigma I. If sigma I is small, we investigate to find out if it remains small over other areas of the design region. And at the end of the experimentation, those factors for which sigma I remains small are considered to have a linear effect, and factors for which sigma I was bigger than a threshold are considered to have a nonlinear effect. At a later stage, although our work essentially stops here, but what could we do with these results? Well, emulator could be simplified with the results. For instance, if the set A indexes those factors that have linear effect, well, we have a suggestion for putting a linear trend in the usual model formulation. It could be even possible, although it's still not, the advantages of it are not very clear, to restrict the stochastic process to those factors that turn out to be nonlinear. So more or less putting the linear bit in terms of the trend, well, the constant term is always there, and then putting only the error for the nonlinear. But we haven't worked a lot on this. Now, this is the algorithm. Essentially, starting with maximin space filling designs, we order the points for, this is a pre-processing stage using a maximum distance, so we have the points ordered. And then we start with 2 points. This is a very rough estimate. We build a trajectory at each of these points, compute the elementary effects, and the moment is just 2 points. But then this is just to screen out all those factors that have an immediate nonlinear effect. This is the threshold, more of which later. And if the quantity, this is coming from the experimentation, if it is bigger than the threshold, we separate the factor, and we have 2 lists in which we are, or 2 baskets if you want, in which we are putting factors that are have linear effects and the factors that have the nonlinear effects. But we only keep the experimentations in those that we are doubtful whether they are linear. So those that have small values of sigma I. And this continues all the way until we have exhausted this candidate set of points. If instead of starting with this finite set of points, a maximum design, we could start with an infinite sequence, like a space filling sequence, and then this procedure could just continue, because here we wouldn't have a final value of the design. But the proposal is just set like this. Now, for selecting the threshold, which is probably the most important component in our method, well, it might be quite hard in certain cases to suggest a value, and we just propose a quite simple approach, which is in sharp contrast to full probabilistic elicitation about beliefs of parameter for a linear model. So just consider, just for this slide and half of the next slide, that we are working with a univariate with a univariate simulator. There is only one input variable. So the effect is modeled, linear or near linear effect is modeled by this regression, where the epsilon i's are independent normal random variables with zero mean and variance gamma. Now, given the variance gamma, then the sampling distribution of the variance of the elementary effects can be calculated according to the following lemma, which in fact looks more complicated than it is, but it's just the sort of material we would normally teach our students of a course like mathematical statistics. Is nothing more than the distribution of the square sums of difference between observations and the mean, which follows a scale chi-square distribution with r-1 degrees of freedom. Remember, again, this should, in all honesty, should have a hat there. Good. What we propose is to use the 99% quantile of this distribution to determine the threshold, so this is a proposal for that. And now what happens in a multivariate setting? Well, this lemma applies directly, and the perform is performed separately per each input variable. Then again, threshold might be fixed for computations rather than adapting to the number of trajectories, that is, adapting to the changing number of trajectories at each step. So if the threshold is kept fixed, the method becomes more conservative in that it is easier to suggest that a factor has a nonlinear effect. Okay, so now I'm moving into the third bit I promised you. This is a rabbit model. So, well, historically, rabbits has been eradicated from large parts of Europe, but there is a remaining risk of reintroduction, and essentially, there is a second vector, which is an invasive raccoon dog that can potentiate the rabies in addition to the usual red fox. Now, this is a simulator, the purpose of which is to analyze the risk of rabies spread in this new type of vector community, which is the raccoon dog. Some characteristic of this simulator is individual-based, non-spatial, time-discrete model, incorporates population and disease dynamical processes, host reproduction, mortality rates, disease transmission. This is not a deterministic simulator, it's a stochastic one. And this reflects the natural variability, for instance, in demographics of these raccoon dogs and the red foxes. Now, model analysis has to contend with stochastic, indeed heteroscedastic model input. And my colleague Alexis Bukubalas has worked on this, modeling both the mean and the variance, but at this point, I am just going to use this model but use a deterministic output. Well, here it is for you. What this model is representing, the raccoon dog and the fox. Now, this model is in program in Java and has an input generating phase, the actual computation of the model, and two types of output, time series and statistics. we have 16 input factors, and for each input factor, the owner of this simulator has specified the range of input values. 3 parameters were kept fixed: number of steps, cross-infection input, and area size. And this is what I just mentioned. I just pick an output which is just deterministic, which is the probability of extinction after 5 years, which is considered to be quite stable. Naturally, this output is hard-bounded in this range, being a probability, and we were suggested that the factor has a near linear effect if the output varies no more than this percentage from linear. So with this sets directly or analysis, this sets the value of gamma. In other words, this quantity was the guiding light. A maximum of 20 design points were considered for the study. And well, as probably here is just better to let the image guide my explanation. In step 1, we are only using 2 runs. So this again, the horizontal axis is mu, and the vertical is sigma. Well, for some reason we have 0 and 1, but this should be 1,000 and well. So this is the threshold, the initial threshold, which means that immediately at this stage, these factors are considered to have a nonlinear, go out of the window. We just continue with one at a time trajectories in what remains. So this is the second step. The second step, you have that the input factor number 2 jumps the fence, and input factor number 5 also does. The threshold is varying with the number of runs we are at. Then, well, a few more steps go. These 4 are still there. We continue investigating them. We continue them. At step 7, 2 of them just finally go. Notice that the threshold is going gradually down. And eventually, final step, these just remain there. So 2 factors were found linear after 20 steps, involving 102 simulator evaluations, and similar results were obtained with a full Morris with 280. Now this is my 4th point, which is this 20-dimensional function. So this was used as a test path. This depends on 20 inputs. The wi's are functions of xi, and analyzing this function, it turns out that only factors x1 to x7 have a nonlinear effect. x8, 9, and 10 have linear effect. The rest, 11 to 20, have negligible effect. I'm just skipping the definition, which values take the coefficient, but it's the same function used in the Morris paper and in Pujol's paper. Now, we set a design again with a maximum of 20 points and repeated our procedure 100 times, during which we identified 99% of the time input factors x1 to x7 as having a nonlinear effect. Now, this should be ... x8 to x20 were identified 95% of the time as having a linear. Mind you, having linear for us in this procedure is the same as negligible. So that was identified 95% of the time with an average of 153 runs, as opposed to 210 runs required for the elementary effects method. Well, just some final discussion. We just proposed this methodology. In the worst case, we will go all the way to the same number of runs as the elementary effects method. We found that it's a good alternative to the elementary effects, and well, these 2 are just prohibitively expensive. We tried this in several simulators. I just presented you the Rabbis model. We also tried this rainfall runoff model, and then we simulated. It might be possible to sequentially run simplexes in varying dimensions, but we haven't tried that. This could be a subject of future work. And also, subject of future work is comparison with other alternatives, as just been pointed out by Jack. This alternative called sequential bifurcation, which in turn, this might be a little bit restricting, but we'll need to talk about that, Jack, because that requires some monotonicity. Now, well, most of this is on this report, which has been just submitted recently, the original paper by Morris. And, well, I think that's all. Thank you.
Okay, any questions for Hugo? No? Everyone wants lunch?
They do.
All right, let's thank Hugo and David again.